So we've calculated the elevator per G to do a pull-up. When we solve that 2x2 problem. And we've talked about how we want this to be a negative number because if we're doing level flight, there's the elevator on the horizontal tail. We want to pull on the stick, which is negative elevator, to pull the nose up, right? The tail pushes down, nose comes up. We want the pilot to be doing that to do a pull-up. So we want that to be negative, not zero, because if it's zero, then there's no feedback to the pilot. And this changes with CM alpha, which depends upon the center of gravity location. Now, other stuff goes into there, like the design of the airplane changes the different parameters in here. But once you build the airplane, the one thing that tends to is the gravity location. And so that's why we always look at that, because you can load the airplane with cargo and people in different locations. So if we want to look at how changing CG affects this feedback, we're going to plug in for CM alpha and then look at the change. So it's how I change the elevator per G. So there's a bunch of algebra, plug in CM alpha, do a bunch of algebra. So we're going to just say, okay, a bunch of algebra here. And we're going to get, substituting in here, we get an equation. Actually, I'm going to switch over to the board. I don't want to kneel down to write this long equation. So I'll let you guys catch up here. So we're going to plug that in up there for CM alpha, factor some stuff out. That's all we're doing is algebra. We're good. I'm going to switch. All right, so here's what we get. You can see here's H minus HN, so that came from CM alpha. And so changing the CG location is going to change the sign of this thing, the stuff in brackets, which is going to change the sign of the whole deal. And so just like the other things, like the neutral point, remember, is the CG location causing CM alpha to be 0. So that's right on the borderline between being stable and unstable. So if you choose that CG position, then you're on the borderline, and that allows us to avoid that position with the CG. So the neutral point is a CG location where pitch stability is neutral, is marginal. We have another location called the maneuver point. It's a CG location where there is no change in elevator with regard to pull up. And so that's the CG location that makes this thing 0. And so that allows us to find another CG location that we need to avoid and stay in front of. And so that's an easy calculation because it's just this set equal to minus that. So we replace H with HM because it's the special CG location. And that's how we calculate it. So we set this to 0, this whole thing to 0, and solve for this. And so just like the CG location neutral point, it's called the maneuver point. And we can have a maneuver margin, case of M for a pull-up. It's how far the CG is in front of this maneuver point. And again, we talked about this before. An analogy in your car would be, we're doing a pull-up, so it's maneuvering, right? So in your car, in the airplane, if the elevator didn't change and you could do a pull-up, that's going to be weird, right? Because you have no feedback as to whether you're doing a pull-up or not. Just like in your car, if you were to turn the steering wheel and go into a turn, but then you'd go back straight with the steering wheel to stay in the turn. That'd be weird. So we want to make sure the pilot has this good feedback. He's going to pull on the stick. And more importantly than this, we'll talk about the stick force. And I talked about that last time, I think, is you want him to have to actually pull rather hard on the stick to pull a lot of G's where he could stress the airplane. So you want to make sure it's physically difficult for him to break the airplane. Yeah. We're going to calculate that for the 182 here in a minute. And we'll find out the answer to that is no. So it's actually easy to avoid this point, but we still have to calculate it. Yeah, so that's next. Good segue into what we're going to do. I need to switch over. So in fact, at this point, we're going to do another in-class assignment. You guys all got up an hour early today. Probably kind of sleepy, right? So hopefully this will get you engaged and you'll be active and your blood will get flowing. Hopefully your brain won't be too mad that I'm having you think this early in the morning. So this will be another one of those things where you're going to write it on a piece of paper and then you're going to submit it and I'll give you 5 points extra credit. If you're on Zoom, you're doing this, there's an item in Blackboard called in-class number 2, and you're going to do that and submit it. Make sure you get that done by 1 o'clock today. Yeah. Submit it virtually to what? Yeah, if you guys have the ability to, if it's your choice. It's actually easier for me to grade this stuff when it's virtually submitted in Blackboard. So if you have, how do you guys submit? Do you use like ScanCam on your phone? Is that what almost everybody does? No, you have a scanner at home, or so if you are more comfortable giving it to me in person right now after we're done, that's totally fine. If you want to scan it in, that's fine as well. Did I not get those others back to the class? Because I need to do that, because that's part of your notes. Yeah. Okay. Where are we? Over here. So the first formula we're going to need is the one I just wrote. So make sure you've got that written down. Let me switch over. We need this one here, and we're going to have to calculate mu and CW. So I'll give you the formulas for that. So we're back to our example airplane. So because we're doing a maneuver, we need numbers for CLQ and CMQ. Remember, this is how the pitch rate, the airplane rotating in pitch, changes the lift and the pitching moment. And we need data on the weight. We'll need that. This is that same cruise flight condition that we've been using all along. Yeah, so we're going to go ahead and we need mu for the formula that we just wrote, and then we're going to need CW in a minute. So let's do both of those now. So CW is really the level flight trim lift coefficient, right? Lift equals weight divided by Q infinity S. And then this mu thing was 2m and you should have everything that you need to calculate that. The mass is going to come from the weight divided by gravity. And then while you're working on that, I'm going to write the formula that you need for HM again. Question, is this 220 or 270? There we go. How are we doing? What are you guys getting for CW? I think we've calculated this before. This would be the lift trim coefficient. You guys getting 0.306? Yeah. Think so. What are you seeing in the book? Let me look. 2m over rho s c bar. Yeah, because that's how it's going to non-dimensionalize, right? Mass per unit volume times volume divided by, or dividing into mass, so that's non-dimensional. For mu, I got 94.36. Oh, I wrote that the wrong place, sorry. This was 0.306, right? And remember, this is really the same CL trim that we had before for level flight. How are we doing on that last formula? You mostly done? So I got for that 0.0671. Positive, and then if you multiply by C bar to get this in feet, so C bar is 4.9, you get 0.3287 feet. And then you have to think, okay, what the heck does that mean? It means the maneuver point distance is bigger than the neutral point distance. So let's draw a picture. Let's move our velocity over here. So all these distances are relative to a datum. So we've got h n times c bar, it's the location of the neutral point. So that's where Cm alpha is 0. And this tells us that the maneuver point is further back because it's a positive number. So the maneuver point is here. And then for this airplane, when we had the CG location, it was given, it's specified. We don't automatically know just from looking at the airplane where the CG is. You have to calculate it. And so when we were doing this example before, the CG was indeed in front of the neutral point. And for this airplane, the maneuver point is behind the neutral point. For most conventional aircraft, that's true, but we still need to calculate. You go, why? Because the pilot is going to want to know how the aircraft behaves when he's doing a pull-up. And if he comes back and he says, hey, this airplane, I was doing a pull-up and it felt really squirrely. I didn't like the feedback. Then you have to go back and figure out, well, what's going on, right? All right, so then we want to calculate the elevator per G. That is, how many degrees does he have to change the elevator to do a maneuver? And the data we're going to need for that. We're going to need, I guess I'm probably better off erasing here, because we're going to need CLQ and CMQ. And we need CW. And we're going to need mu, I think. See, we're done with all that stuff, I think. So you guys caught up here and on Zoom, caught up that I can erase some of this? We're good? You'll see in a minute. Because we're going to say, all right, let's do a 3G pull-up. How fast is the airplane rotating? How fast, if we do a pull-up and do a full circle at that same pull-up rate, how long does it take? So just to get a feel for how fast this pull-up is happening. So let's do a 3G pull-up. Again, we're doing this at 220 feet per second. And so I want to calculate Q. And what we have is this non-dimensional Q in terms of load factor. So there's why we needed CW. Right, and this, we calculated this by plugging in Q into this formula in terms of load factor, and we got that. So let's calculate this. What is this thing? Because that's going to give us radians per second, and then we're going to convert it to degrees per second, and then we're going to find out how long it takes to go a full 360. So what do you need to do this? You need mu, which we did. You need CW. You need N. C bar, you guys have that as 4.9, right? And the velocity is 220. So hopefully you're getting a number like 0.2912. And if you work the units on this, it comes out dimensionless. So that's how you know that it's radians. And then this turns out to be 16.68 degrees per second. So that means you got 19. Did you get this? What did I do? You put in 3 here. Let's check it out. It's entirely possible that I did something wrong here. You got that? Oh, okay, happens, yeah. And so how long does it take to do a full 360 circle? Just to get a feel for this. So 360 degrees divided by 16.68 degrees per second. The degrees are going to cancel out. We're going to get seconds. Just to get a feel for this, it takes 16 seconds. Now we've analyzed this at the bottom of the pull-up, so it's a bit fictitious, but if you maintain that pitch rate all the way around in a full circle, it would take you 16 seconds, which seems kind of reasonable if you think about an aerobatic airplane doing this kind of thing. So again, that's just to give us a feel. We're not rapidly rotating with the airplane, but we are rotating the airplane as it does this maneuver. Did I do that wrong? Oh, jeez. Yeah, you're right. I was looking at the wrong number. Okay, 21 seconds. Thanks for checking me. All right, so the last thing we want to do with this is calculate how many degrees of elevator per g. So we're going to calculate delta delta E over n minus 1. So the data we need for that is CLQ and CMQ, and the determinant, and CM alpha and CL alpha. So get these numbers down on your paper, then we're going to switch to the other board. I'm going to give you the other numbers that we had from before, and then we'll calculate. So we need the determinant that we calculated from before for the 2x2 trim problem. And then we had CM alpha and CL alpha from back then, because we calculated them. Right, that's the curve slope of the entire airplane. This is the pitch stability of the airplane that we calculated in homework and for this example. And now we need the big formula. And you guys should have CW and mu from before, and CLQ from before. Kind of a big formula, but you guys are good at this, right? All right, we got mu. We just calculated that, so you should have that on your paper. CW, I gave the determinant. CLQ and CMQ were from the previous board that you wrote down. And then CL alpha, CM alpha come from there. So we're doing this for the 3G pull-up, so that's saying delta delta E over 2 minus 1. Stuff it into that formula and should get minus 0.058 radians per G, or 3.32 negative sign degrees per G. Should be what? Oh yeah, 3 minus 1 is 2, sorry. And then, yeah, I divided by 2, right? So that means that for every G that he pulls, the elevator is going to change by 3 degrees, which is not a ton, but it is a movement on the stick. That's, for an elevator, that's a significant movement. So this is position feedback. So stick position feedback. So the pilot has to move the stick to a different position to do a pull-up. That's good. Just like the steering wheel, you have to move to a different position to do a turn in your car. Pardon, what? Yeah, because that means that you have to pull on the stick, right? Let's draw the picture again. There's level flight. We want to pull on the stick. That's a pitch. If the elevator goes negative delta, that's the direction to cause the nose to pitch up, and that's the motion you're doing when you're doing the pull up. And that's connected to the stick of, my stick's kind of short, of moving backward like that. So yeah, this is good feedback. Now the other thing we have to look at is how much stick force. Because if there's no force that the pilot has to give on the stick, he can just take his finger, pull back on the stick real easily, and pull 20 Gs and break the wing, like we were talking about. So we want to make sure that there's significant stick force per G as well. And so then we have to get the hinge moment on that elevator when he's doing the pull-up. And of course, that's going to depend upon the trim tab. So we're going to do the same thing we did before. We're going to look at the level flight trim tab, hinge moment, and the pull-up, and look at the difference in stick force. Because we want the pilot to have to generate a force, a significant force, to pull on the stick. Just like to hold your car in a turn, the faster you're going, you have to actually create some force on the steering wheel to keep it in the turn, right? If you're in a turn and you let go of your wheel, it doesn't stay there, hopefully. The car will actually want to return back to straight, right? You believe me? You've experienced this, right? If you're going down the interstate, you're in a turn. If you're doing a turn onto another street, if you let go halfway through the turn, the car is not going to do the turn, right? Same deal here. You get that feedback. It also tends to want to straighten itself back up, which is what's happening here. If you're in a pull-up and you let go of the stick's going to go back to 0 stick position, and so you'll come out of the pull-up. And like everything else, a lot of this stuff was discovered along the way with airplanes. You know, they build an airplane and they get it off the ground, fly for 12 seconds, all right, brothers, land, and then later on they found out that that airplane was marginally or maybe a little bit pitch unstable, and so it was hard to fly. So then they started looking at, well, how can we make it easier to fly? They discovered this kind of stuff along the way as well. Our job as engineers and scientists is to discover this hopefully ahead of time before it's a catastrophe. Kind of like we want to figure out what the people need if we send them to Mars and they're going to have to stay there for 6 months. What do they need? What is their habitat going to survive the winds and all that stuff? All right, so control force per G is what we want to do. So P is stick force. And that's the gearing times the hinge moment coefficient. And the hinge moment is simply the force of the air pushing on the elevator in its deflected position. That's all it is, and we know how to calculate that. And so what we're going to focus on is the hinge moment coefficient, and we're going to look at CHE in level flight before he starts doing the pull-up. I switched the camera over here, right? Yep. So in level flight, we're going to say we're trimmed stick force. So we're going to do the trim tab to give us 0 stick force. So we're saying the pilot took off, he's cruising along, move the trim tab so that he doesn't have to pull on the stick all the time when he's cruising along. And now he wants to do a pull-up. So level flight, everything's trimmed out. This is trim alpha, trim elevator that we solved from the lift and the pitching moment equation. And now we're going to do a pull-up. We're going to get a different hinge moment because we're going to trim at a different angle of attack. Just like before, here's the extra angle of attack we need to do the pull-up. Here's the extra elevator we need to do the pull-up. And we're not changing the trim tab because we're just going to do this as a quick pull-up, so the pilot's not going to change the trim tab. So there's our analysis of the stick change in the stick force per G. Sorry, this is going to be 0 plus delta. Because we had 0 up here, so the change during the pull-up is this here. So there's level flight during the pull-up, the stick force changes, alpha changes, elevator changes, trim tab does not change. And just like before, we're going to calculate that change by subtracting the top one from the bottom one. And stuff is going to cancel out. Just like before, we're going to subtract this from this, and then we're going to get how the stick force hinge moment changes when we do the pull-up. Make sense? Oh, I just realized I forgot something. What did I forget on here in the pull-up? Remember what we had in the lift and pitching moment? Yeah, the cue effect. So I need to add that in here. Because we're pitching, so we have some hinge moment. It's on my paper, I just didn't look at it. So we have to add that in. And that's going to be in here in the delta. Because it's only there during the pull-up and not in the level flight. And then this is the trim extra alpha, and this is the trim extra elevator. And so we're going to substitute in from those solutions that we had before. If you look back at them, remember the formula we had for this is this big long thing, right? So this is a big long formula we're going to get for how this changes with elevator. So after you do all that algebra, divide by n minus 1, because there's n minus 1s there. And this A prime thing that shows up there is that thing. How we doing on time? 14. Yep. So a little side note, if you were given this formula and the formulas for this, and you had to do the algebra and make sure you were right, what would you do? You have a strategy? If I said, go home, do this, bring it back. If you get it right, I'll give you $100. How would you make sure you had it right? I don't hear anybody. Any thoughts? Because you may end up having to do this at a job, right? Where you have to come up with this. And they need to know this for the airplane before it flight tests. In fact, I had to do something like this. I worked on the AV8B, the Harrier, and the pilot needed to know at what airspeed he rotated the nozzles downward to do a short takeoff. So they gave me charts, and I'm like freaked out because here's the pilot, and he's going to be going down the runway, and he's going to rotate the nozzles at the airspeed that I tell him to turn them at. So what did I do? I did the calculations, found out the number, and then I talked to 3 other people in the same group who had done this before and just double checked my numbers, right? And then the pilot, of course, had flown this airplane before. So when we were in the flight briefing, I say, here's the number, does this make sense? And he goes, oh yeah, that seems similar to what we've done before. So you check this stuff out. So how could you make sure you did your algebra right here? Yeah, check it out. Have other people do it, show your work to somebody else, have them check it. And you guys, Dr. Yang teaches you how to do Maple, right? So it does algebraic calculations as well. I don't know Maple. I mean, there are other symbolic manipulation programs where you can feed them formulas and tell it to do this, and you can double check it. Does Maple do that? Yeah, so you could do that to check it out. You go what? Oh, okay. Is control with G. No, what you're going to turn in is just the numerical calculations that we've done today. This is 5 points extra credit. It's 5 out of 0. Hopefully you're not trying to decide whether it's worth your time doing it, but yeah, this is for your benefit. This gets you engaged, and hopefully you've done this. Okay, last thing, guess what? We want stick force per G to be positive. We want the pilot to have to pull. So a bad situation would be when this is 0, right? Just like in your car, to do a turn, it takes no force at all to go into the turn. We don't want to do a pull-up where there's 0 stick force per G. Guess what? There is a CG location where hinge moment per G or stick force per G is 0, and that's another bad location that we want to avoid. And it's given by this, setting this formula equal to 0. Do I have time to write this on the board? Yes, I do, 2 minutes. So we'll stop there. And it's different than HM before, but we're still doing a maneuver. What do we want to call this? This is going to be the CG location where stick force or hinge moment per G is 0. So what do we want to call it? For like a university, we find some donor that donates $10 million and we name it after them, right? But we want to name it something that makes sense. It's going to be a maneuver point because we're doing a maneuver. But what's different here? Before, we were just looking at elevator position, and now we're talking about the stick force. So we don't want the pilot to be able to just let go of the stick and do a maneuver. So we call this the stick-free maneuver point. And that other thing that is called the stick fixed, because the pilot's holding the elevator where it needs to be. Yeah, so more terminology, I know, but it's important stuff for airplanes. So that is where we'll stop today. That's the definition. The stick fixed maneuver point is where elevator per G is 0, and the stick free is where the stick force per G is 0. And we want to avoid both of those. So next time we'll calculate this. For our example airplane. All right, have a good rest of your day. I'll see you guys on Zoom on Wednesday. Yep. Oh, sorry. This is what's called HM prime. Yeah. So this is the stick free, and it's just showing how it is relative to the stick fixed. Everything, what was the last calculation we did? We did delta delta E over n minus 1. Yeah, that is the n.